Laws of refraction of light. First law of refraction of light: the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane. Second law of refraction of light. It is also called as Snell's law of refraction of light. The ratio of sine of angle of incidence to the sine of angle of refraction is constant for a given pair of media. That is, sine of angle of incidence upon sine of angle of refraction is equal to constant. It is written as sin small I upon sin small r is equal to constant. The constant is also called as refractive index. The value of the constant sin I upon sin r for a ray of light passing from air into a particular medium is called the refractive index of that medium. The refractive index is denoted by symbol small n. Thus, refractive index small n is equal to sine small I upon sine small r, where sine I is the sine of the angle of incidence in air, sine r is equal to sine of angle of refraction in medium. Since the refractive index is a ratio of two similar quantities, the sines of angles, it has no units. Refractive index and speed of light. The refractive index small n can also be written as a ratio of speed of light in two media. The refractive index of medium 2 with respect to medium 1 is the equal to ratio of speed of light in medium 1 to speed of light in medium 2. This can be written in the form of equation as medium 1 refractive index medium 2 is equal to speed of light in medium 1 upon speed of light in medium 2. The speed of light is denoted by small v. So, subscript 1 small n subscript 2 is equal to v1 upon v2, where v1 is speed of light in medium 1, v2 is speed of light in medium 2, and subscript 1 and subscript 2 is equal to refractive index of medium 2 with respect to medium 1. When light is going from one medium to another medium, then the value of refractive index is called relative reflective index or relative refractive index. When light is going from vacuum to another medium, then the value of refractive index is called absolute refractive index. The refractive index of a medium with respect to air is also considered as absolute refractive index. The ratio of speed of light in vacuum to speed of light in a medium is called refractive index of that medium, which we have already seen. The formula for refractive index of a medium is equal to speed of light in vacuum upon speed of light in medium. Since the speed of light in air is almost equal to the speed of light in vacuum, so for all practical purposes, we say that the ratio of speed of light in air to the speed of light in medium is called refractive index of that medium. Thus, refractive index of a medium is equal to speed of light in air upon speed of light in medium. If we take an example of glass as the medium and use glass as the medium in this equation, we can write it as a refractive index of glass is equal to speed of light in air upon speed of light in glass. The speed of light is 3 into 10 raised to the power of 8 meters per second, and speed of light in glass is 2 into 10 raised to 8 meter per second. So the refractive index of glass is equal to 3 into 10 raised to 8 upon 2 into 10 raised to 8. Thus it is 3 by 2 is equal to 1.5. Thus the refractive index of glass becomes 1.5. By saying that the refractive index of glass is 1.5, we mean that the ratio of speed of light in air to the speed of light in glass is equal to 1.5. The refractive index depends on the nature of the material of the medium and on the wavelength of the light used. The refractive index values of different materials have been obtained by using yellow sodium light of wavelength 589 nanometer or 5.89 into 10 raised to the power of -7 meters. We must remember that if any two media are optically exactly the same, then no bending of light occurs when light enters into it. A substance having higher refractive index is optically denser than the substance having lower refractive index. As an example, refractive index of glass in the previous example is 1.5 and that of water is 1.3. Since glass has a higher refractive index than water, therefore glass is optically denser than water, and more bending of light takes place in glass than in water. It means that higher the refractive index of a substance, it changes the direction of beam of light more passing through it. The optical density of a substance is different from its mass density. The refractive index for light going from medium 1 to medium 2 is equal to the reciprocal of the refractive index for light going from medium 2 to medium 1. Refraction of light by spherical lenses. The working of a lens is based on refraction of light rays when they pass through it. A lens is a piece of transparent glass bound by two spherical surfaces. There are two types of lenses, convex lens and concave lens. A convex lens is thick at the center and thinner at the edges. A concave lens is thin in the middle but thicker at the edges. Optical center and principal axis of a lens. The center point of a lens is known as its optical center. The principal axis of a lens is a line passing through the optical center of the lens and perpendicular to both the faces of the lens. Principal focus and focal length of a convex lens. The principal focus of a convex lens is a point on its principal axis to which light rays parallel to the principal axis converge after passing through the lens. A lens has two foci. The two foci of a lens are at equal distance from the optical center, one on either side of the lens. A convex lens has real focus. The focal length of a lens is the distance between optical center and principal focus of the lens. A convex lens is also known as converging lens because it converges a parallel beam of light rays passing through it. Principal focus and focal length of a concave lens. A convex lens converges a parallel beam of light. A concave lens diverges a parallel beam of light rays. The principal focus of a concave lens is a point on its principal axis from which light rays originally parallel to the axis appear to diverge after passing through the concave lens. The concave lens is also known as diverging lens because it diverges a parallel beam of light rays. A concave lens has a virtual focus. The image formed at a point where at least two refracted light rays meet is the point, and there are rules for obtaining images by convex lenses. Rule 1: a ray of light which is parallel to the principal axis of a convex lens passes through its focus after refraction through the lens. Rule 2: a ray of light passing through the optical center of a convex lens goes straight after refraction through the lens. Rule 3: a ray of light passing through the focus of a convex lens becomes parallel to its principal axis after refraction through the lens. Formation of different types of images by a convex lens. The type of image formed by a convex lens depends on the position of the object in front of the lens. The different positions of the object are: 1. Between the optical center and the focus, 2. At the focus, 3. Between focus and 2f double focus, 4. At 2f means a distance which is double that of focal length, beyond 2f, and at infinity. We consider all these 6 positions one by one. Position 1: image formed by a convex lens when the object is placed between optical center and focus. Object is between C and F. C is the optical center of the lens and F is the focus point of the lens. When the object is placed within the focus of a convex lens, the image formed is behind the object on the left side of the lens, virtual and erect, and larger than the object. An example is a convex lens being used as a magnifying glass to read small print of a book, or a convex lens producing a magnified image of middle part of any object held behind the lens. Smaller the focal length of a convex lens, greater will be its magnifying power. Position number 2: when the object is placed at the focus of a convex lens or the object is at F, capital F. So when an object is placed at the focus of a convex lens, the image formed is at infinity. It is real and inverted and highly enlarged. Position 3: when the object is between focus and the distance double that of focal length, that is 2f. So the object is between f and 2f. When the object is placed between f and 2f in front of a convex lens, the image formed is beyond 2f. It is real and inverted and larger than the object. When the object is kept at 2f position, then the image formed is at a distance of 2f on the other side of the lens, real and inverted, of the same size as the object. Position number 5, when the object is beyond 2f. When the object is placed beyond 2f in front of convex lens, then the image formed is between f and 2f on the other side of the lens, real and inverted, smaller than the object. Example is a bulb placed in front of a convex lens and a screen placed behind the convex lens. The bulb is placed at a distance more than twice the focal length from the convex lens. Here, the convex lens forms a real, inverted and diminished image of the filament of a light bulb. Position number 6, when the object is at infinity. When the object is at infinity from a convex lens, then the image formed is at the focus, real and inverted, and much smaller than the object. When object is at infinity, the distance of image from the lens will be equal to the focal length of the lens. Uses of convex lenses. Convex lenses are used in spectacles for long-sightedness. Convex lens is also used for making simple camera. Convex lens is used as magnifying glass. Convex lens is also used in making microscopes, telescopes and slide projectors or film projectors.